Imagine asking an AI browser to compare 3 software plans. It reads the features and starts building a recommendation. Then one page contains text designed to redirect the agent. You never type that instruction, but the agent processes it alongside your request. If that browser can click submit forms, download files, or reach connected accounts, web pages, no longer just information. It may influence a system that can act. That is the hidden security problem behind indirect prompt injection. A normal browser displays information and waits for you. A browser agent adds reasoning and action. It can interpret a goal, navigate pages, compare options, fill fields, and continue through a multi-step task. That is useful, but it changes the security model. The system is feeding untrusted web content into a model that may choose the next action. The question becomes, what can the agent see? What can it do? And when must it stop for approval? Direct prompt injection starts in the conversation. When a user tries to override the model's rules or redirect the task, indirect prompt injection arrives through external content such as a web page, document, email, or advertisement. The agent did not receive it as the user's request, but may still parse it as an instruction. Delta browsing requires the system to consume content from places it does not control. OpenAI, Anthropic, and Chrome's agent security guidance all treat untrusted external content as a risk boundary. The page is data. The agent must not silently promote that data into authority. Here's a sanitized fictional example. A user asks an agent to compare 3 project management plans for a 5-person team. The agent collects price, storage, collaboration features, and cancellation terms. The user expects a summary, not a purchase. The task only needs public product information, not private files, saved passwords, internal dashboards, or form submission. That is the intended boundary. Every capability outside it creates impact the task never needed. On the second fictional page, content includes a malicious instruction disguised as ordinary text. We will keep the wording sanitized. Its purpose is to make the agent leave the comparison task and access unrelated information. The page may sound authoritative or claim another step is required. A person watching the pricing table may miss it, while the agent processes the full page. The important point is not one to exploit. Outside content is competing with the user's trusted goal inside the same reasoning context. Suppose the agent follows that redirect. A weakly constrained system might open a connected workspace, copy information, or place it into a form. Safer design interrupts the chain before a sensitive action completes. Even if detection fails, permissions should block unrelated data. If access exists, an approval gate should stop disclosure, submission, purchase, download, or settings changes. Here, the agent pauses and explains the action. The user rejects it. Nothing sensitive leaves the environment, and the attempt becomes a logged security event instead of an incident. The core problem is a confused trust boundary. The agent receives a trusted user request and untrusted web content, but both may appear as language inside one decision process. Models can distinguish an instruction from text describing one, but that distinction is not perfect when content is crafted to manipulate the task. Detection helps, yet no single classifier or prompt guarantees immunity. The durable goal is to preserve user intent while limiting what manipulated content can cause. The same injection attempt can produce very different outcomes depending on the agent's access. With read-only access to one public tab, the result may be a wrong summary or a disrupted task. Add save sessions, private cloud data form submission, downloads, code execution, or internal network access, and the possible impact grows. Not every browser agent will perform those actions, and not every injection succeeds. Capability still creates a blast radius. Security teams should identify reachable data, available tools, high impact actions, and steps requiring independent confirmation. The risk is not only what the model says, it is what the surrounding system allows the model to do. Start with least privilege. Give the agent only the data and tools required for the current task for only as long as the task requires them. A comparison task needs public page access and a place to write a summary. It does not need an email account, a password manager, private documents, or the ability to submit forms. Prefer read-only connections when possible. Separate research from execution. Use short-lived credentials and task-specific scopes instead of broad standing access. This defense does not depend on perfect prompt injection detection. If the agent is manipulated, the available action set is already narrow. Least privilege turns a potentially dangerous detour into a constrained failure. Place explicit approval gates before consequential actions, such as sending data, submitting a form, confirming a purchase, changing settings, downloading an executable, or opening a sensitive system. The prompt should explain the action, destination, data involved, and reason. That context helps the user notice when a step does not match the original goal. Enforce the gate in the tool layer, not only in the agent's prompt. The agent may propose an action, but a separate control decides whether it is permitted. Isolation reduces what untrusted browsing can reach. Run higher risk research in a separate profile or sandbox without personal sessions. Save credentials, private extensions, or unrestricted internal access. If a login is required, use a narrowly scoped account instead of an administrator identity. Control downloads and prevent automatic execution. Isolation assumes some pages will be hostile or misleading, then designs the environment so one compromised task cannot easily cross into production systems or private data. Monitoring makes agent behavior reviewable. Record pages accessed, tools called, sensitive actions attempted, approvals requested, and whether each action was allowed or blocked. Preserve enough context to reconstruct the sequence without storing unnecessary sensitive data. Alert on meaningful signals, such as an unrelated domain, a new data source, repeated approvals, or content trying to override the user's objective. Teams can use near misses to tighten permissions, update policy, and test in Delta whether the controls stop the pattern next time. Before giving an AI browser a real task, use this checklist. First, define the intended outcome and the exact actions the task requires. Second, remove every account, tool, and data source that is not necessary. Third, treat web pages, emails, documents, and advertisements as untrusted input. Fourth, require clear approval for disclosure, submission, purchase, download, configuration change, or access to private systems. Fifth, isolate unfamiliar browsing from personal and production environments. Sixth, log tool calls and review unexpected detours. Seventh, test the controls with harmless simulated injections before relying on the agent for important work. And finally, keep a human accountable for high-impact decisions. Useful automation should reduce effort, not erase responsibility. AI browsers are powerful because they can move from reading to acting. That same ability makes trust boundaries, permissions, and visibility essential. Prompt injection detection will continue to improve, but safe adoption should not depend on perfect detection. Narrow the agent's access. Stop before sensitive actions, isolate untrusted browsing, log what happens. If you are finding this content useful, please subscribe, like, and comment. The goal is not to fear AI agents. It is to give them enough freedom to be useful, with enough boundaries to remain under human control. Build the capability carefully, verify the controls, and let security grow with the automation.